Okay, in chapter 9 we have seen phase diagrams, and we understood how to interpret the phase diagrams to figure out what phases we have at a given concentration and at a given temperature in a material, and how we can change the phases from one phase to another by just cooling down the material or heating it up. So in this chapter we're gonna take a look at how these phase transformations are happening. So we have learned that there are several ways to increase the strength or change the mechanical properties of the material. We have seen grain size refinement, solid solution strengthening, and we have seen strain hardening. And we also know, so these all three methods to change the mechanical properties of the materials, they all depend on changing the microstructure, because we have learned that the microstructure actually controls the mechanical properties of the materials. So if we change the microstructure, we change how this microstructure interact with the dislocation, how it prevents dislocation motion, and therefore strengthens the material. And there is another way here we're going to see. We also can obtain different phases of the same alloy, and this can also provide changes to the mechanical property of a material. How do we achieve phase transformations? We do heat treatment. So heat treatment means either cool the material down, or heat it up and obtain certain phases inside the material. What if we cool it? What if the cooling rate affects the microstructure, for example? What if we cool it very fast? Because remember I told you phase diagrams are obtained assuming the structure reaching equilibrium conditions, meaning we provide a lot of time for the system to reach its thermodynamically stable phase. But it always takes time to reach that phase that is predicted with the phase diagram. If we do the cooling very fast, that means we are not providing enough time for this atomic species to diffuse into their nucleation sites, to diffuse into their stable configuration. So maybe there are phases we can obtain, but not shown in the phase diagrams. We call them non-equilibrium structures. Maybe they can form, and they also can show different mechanical properties which are useful to us, which are desirable. So therefore in this chapter we're gonna study this phase transformation and how the time and temperature will affect the rate of transformation, the structures that are forming. And is it possible to obtain non-equilibrium structures, as I said, is structures that are not predicted by the phase diagram, because the phase diagram is always showing us equilibrium structures. And how about the mechanical properties? If we have certain non-equilibrium structures forming, are they going to have more desirable properties compared to the ones that are in equilibrium ones? Okay, so we're all going to see that and in this chapter. So now we have learned that phase transformations are important because we have studied phase diagrams, and we have seen different phases will have different microstructures and therefore different properties. So what type of property we desire, maybe we can play with the phases inside the material and we can achieve those desirable properties. So therefore it is important to understand how these phase transformations are happening, and is there a way to control them by changing time, temperature, and maybe other parameters. So phase transformation, they don't happen instantaneously. Suppose you're going from liquid phase to solid phase, right? This doesn't happen immediately. There are stages. The first thing that happens is nucleation. Okay, so that means nucleation means very small particles of or nuclei of these new phases will start to form, and then these will start to grow in the second stage. So the first stage is nucleation, and the other stage is growth. So in the nucleation stage, first tiny nuclei will form. We call it also seeds. These are going to be the templates where the crystals will start to grow. So these crystals, like, think about grains, right? Different grain, different crystals. They're gonna all start from starting to grow from a tiny nuclei. But this nuclei has to be energetically stable. So nuclei can dissolve back to liquid. It can keep growing. So how do we determine if it's going to continue to grow or if it's going to dissolve back to liquid? So these are all energetically favorable conditions. If those conditions happen, then the nuclei will start to grow. So these are related to energetics, or of course when we talk about energy we are talking about thermodynamics. That's why I always say if something is thermodynamically stable, it will continue to grow, right? Or what we are seeing in the phase diagrams are thermodynamically stable phases, meaning the equilibrium is reached in that system. So the tiny nuclei will form first, and these nuclei of this new phase that is forming from the liquid, they can be just few hundred of atoms, so very tiny, and which can grow, but it might not be grow. You need to achieve certain energetic factors that for this nuclei to grow into a larger size. The larger size, the stable size of this nuclei, where it will continue to grow, is going to be called nucleus. Okay, so for the nucleus to form, the atoms needs to be added to the nuclei. And for this to happen, of course, the rate of addition of the atoms to the nucleus must be faster than the rate of loss for this nucleus now to be stable and keep continued growing. So once this nucleus form, which we can say the stable structure now, it is capable of growing now, and growth will proceed until equilibrium is reached, meaning until the equilibrium phases is achieved. So the phases that are shown with the phase diagrams, right? Those were the equilibrium phases. Okay, so we're gonna see these concepts in the next slides. How a nuclei becomes stable, and how it is called a nucleus, and how it is capable of growing based on the energetics of this process. So we're gonna see that actually how can we there is a driving force, how we can increase the nucleation. There are factors affecting that, and one of them is degree of cooling. So delta T, that means how much you are away from the melting temperature of that system. So if we say supercooling, how much we are below the melting temperature of that system. Okay, so, or if you say superheating, how much you are above the melting temperature of that system. So that degree of supercooling or superheating in different systems is going to be the driving force. And if you increase this, if you, let's say for the supercooling, how much we are below the melting temperature. So we can say melting temperature minus the temperature we're at. Okay, this is the degree of supercooling. So if you have a large supercooling, you have rapid nucleation rate. You will have many nuclei. So this, if this is background is liquid, these are the nuclei forming, right? Tiny particles, small crystals forming that are capable of growing. So if you have delta T, which is large, you go way below the melting temperature. When you cool it down, that means you are giving the material to have many nuclei forming, and then it is also, there is rapid nucleation rate. On the other hand, if there is small supercooling, you just go a little bit below the melting temperature of the system. That is actually the driving force is low here, so there is going to be slow nucleation rate, only few nuclei, okay, and those will capable of growing. Okay, so only let's say few. Okay, but if you have so many, that means these are large, forming large crystals. If you have a super slow cooling rate, few nuclei, they will grow into large crystals. But if you have so many nuclei that you achieved with a large supercooling, then these are all gonna grow, and you will have so small crystals and many nuclei. Okay, so we're gonna see this also in the next slides. We're gonna look at how we can thermodynamically explain how a nuclei becomes stable enough to continue growing and not dissolve back into the liquid. So there are two types of nucleation, and one is homogeneous nucleation. The difference between them comes from where the nucleation events happen. Okay, in the homogeneous type, the nuclei of the new phase form uniformly throughout the parent phase. Okay, so for this you need a large driving force. Okay, so your degree of supercooling should be relatively high, like that delta T, like should be in between 80 and 300 degrees C. That means you should be go up below the melting temperature up to 300 degrees C. So that requires a large driving force. Okay, and there is the heterogeneous nucleation. This is nuclei formed preferentially at structural inhomogeneities such as surfaces, impurities, grain boundaries, dislocations. Why? Think about this. Remember, let's say grain boundaries, because I remember I mentioned that in the phase diagrams, the new phase was starting to form at the grain boundaries. And you should ask yourself why. Right, because remember, the grain boundaries, atoms are less packed, they are more energetic, they have more energy, they want to react. So they are providing these energy sites for these nucleides to become more stable. Therefore, if there are grain boundaries, impurities, defects, those are all energy sites. There is a strain. Remember, atoms are disordered, they are strained, they have strain energy. So this energy can be used in the nucleation and making the nuclei more stable and making it continue to grow. Therefore, this will require less supercooling, very tiny supercooling, because you already have energy on those nucleation sites that is provided for the nucleation and growth to happen. Therefore, people usually, when they want to reduce this delta T, degree of supercooling, they can add intentionally some impurities to start the nucleation inside. So they can control the solidification process by intentionally adding some impurities in the system. So again, there is two types, homogeneous and heterogeneous. And let's now look at them. Now, there is important thermodynamic parameter when we are trying to explain the homogeneous nucleation and energies. You need to understand what is free energy. Free energy is shown with a symbol G. Okay, this is also called Gibbs free energy. This Gibbs free energy is related to thermodynamic parameters like enthalpy, entropy. So we are not going to, of course, go into the thermodynamical principles behind this free energy. More advanced topics, more advanced material science topics, maybe you can cover that. But what we need to understand about free energy is when it comes to phase transformations, going from one phase to another. This can only happen, this transformation only happens spontaneously when the delta G has a negative volume. So going from one phase, the free energy of one phase has to be lower than the free energy of the other phase. So the change has to be negative. Okay. So if delta G has a negative volume, then this transformation will happen spontaneously. It also means you are going to a more stable phase. The energy is much less. That is how the nature works, right? So whenever a system is more stable at those conditions, we see that configuration in nature. So therefore, if the energy is minimum, that means it's more stable. It's a stable phase. So therefore, we conclude that when the delta G has a negative volume, then the transformation happens by itself spontaneously. Okay. All right. There are two contributions to the total free energy change, delta G. We can say delta G or delta GT, the total free energy change. And we want this to be negative for our nuclei to be stable and then continue to grow. Okay? So what are these two factors that are affecting the total free energy change? So one is the volume free energy with a subscript V. Okay. The volume free energy change. So we are going from liquid solidifying into the solid, right? So new nuclei are forming. Okay, so this is background is, let's say, liquid. This is the nuclei. Excellent. That is forming within the liquid because I'm cooling the material down. So I need to make sure this nuclei reaches a stable amount and then continue to grow, right? So there are two factors that are affecting that. The first one is the free energy difference between the solid and the liquid. This is the volume free energy. So as you can see in the graph, the volume free energy is shown with the blue, and as you can see, it is as the radius of this nuclei keeps increasing, the volume free energy is decreasing. So it is actually making it stable, because that's what we want, right? We want the free energy to go to negative, to decrease. So when it's decreased, it's getting smaller. That means the material is becoming more stable, the nuclei becoming more stable. So the volume free energy is basically the difference between the free energy of the liquid and the solid. Okay, we are going from liquid to solid. There is another contribution to the energy, which is the surface energy, because as this nuclei keeps growing, there will be energy related to the surface of it. Okay, it's the surface, the boundary between the liquid and the solid. So surface energy is shown with gamma here, And as you can see, the red, the surface energy, as we increase the radius of the nuclei, you see that the free energy change becoming positive. That is something then negatively affecting the nuclei to become stable, because we want to go to negative values. However, the formation of new surfaces unfortunately trying to destabilize the nuclei, making it unstable. So then we need to find this balance between the surface energy and volume free energy, and the sum of them, because there is two contribution, remember, to the free energy change, the total free energy change, and that is the surface free energy change and the volume free energy change, and the sum of them has to be going to decreasing. Delta G has to be decreasing in order for that nuclei to become stable. So first, the surface tension, the gamma term, is actually defined as the surface energy per area. Therefore, what is the area of a sphere? Area of a sphere, assuming the nuclei is a sphere, right? Area of a sphere is 4 times pi times r squared. Then if this is surface energy per area, I need to multiply with the area to find the overall surface energy change, free energy change. The same thing you do for the volume free energy. This was volume free energy per volume, okay, and then you need to multiply it with the volume to find the volume free energy, right? So the volume is for a sphere, assuming it's the nuclei spherical, volume of a sphere is 4 over 3 pi r cubed. So therefore these two things are affecting the total free energy. So this is the equation of that curve, this is the equation of that curve, and what about the sum of these curves is shown with a green here, as you can see, okay? As you can see, this delta G reaches a maximum at a certain radius of this nuclei. Okay, so up until that is called R star, the critical radius, the critical nucleus size. Okay, critical nucleus size. Up until that point, you can see that the free energy is increasing. So that means that if the nuclei cannot reach that size, the critical nucleus size, and always stay below that size, it will never reach that thermodynamically stable size to continue to grow. It will dissolve back, because energetically it is not stable. But once we pass that R star, the critical nucleus, we go above. If we are below, the nuclei will dissolve back. But if we go above that R star, the critical nucleus, as you can see, delta G is decreasing, meaning that this term here becoming more dominant, and it is decreasing the total free energy, and therefore as we are decreasing the free energy. That means the structure is becoming more stable. Therefore, once you pass that R star, the nuclei will continue to grow. It is now thermodynamically, energetically stable. So therefore, actually, when you have particles, the nuclei, when it reaches R star, it is now called, when it reaches R star and go above, it is now called nucleus. That means it's stable, it's now going to continue to grow. And R star is therefore the critical nucleus size. Delta G star, which is at this point, right? Delta G star you are reading from here at the critical nucleus size. The delta G star is gonna be the critical free energy change. So critical free energy. The delta G star is giving us actually the activation free energy, which is the free energy required for the formation of stable nucleus. You can also think about it as an energy barrier to the nucleation process. Alright, now let me add a page here. Okay. Oh, okay, so let's now derive equations for R star and delta G star. Okay, so activation energy and critical radius. Okay, let me get a good pen here, pen color. Okay, so now we learned that the delta G is equal to the sum of the free energy changes related to the surface and the volume free energies. Okay. So this was delta G S, right? And this was total. Okay. Alright, so this is a different V, a little bit different here, you can see. Okay. And now if this is the equation for this curve, right? This one. This is the equation for this curve here. So if I actually take the derivative and set it to 0, it's gonna, because at this point the derivative of this curve is 0, and that will happen when I'm at R star. Okay, so I can set this to 0, taking the derivative and placing R star instead of R. So what I can say that then delta dd, this one is equal to 0 when I have R star. Wait, you're gonna take the derivative. So this is wrong. So you need to take the derivative, right? So derivative of this is gonna be root 3 pi r squared. So derivative of this. This is not t, of course. Where did this come from? Okay. All right. So we take the derivative of this equation, and then we continue with the second term here, 4 pi r. No, not 2r, right? 2r. 2r. And this, which is equal to 0, we said. Okay, and this r is gonna be the r star. And let's plug in r star and then solve it for the r star. Actually, let me do this, which is equal to minus 1 pi. Okay, so we found our equation for the critical nucleus size, which the book also calls it critical radius. Okay. So we found that equation. Now, if you go to your equation of the free energy change and plug in this value here, that will give you the delta G star here, because in your curve, right, when you reach the R star, when this curve at the place of R star in the x-axis, it will give you in the y-axis the delta G star. Let me open up new page here. Okay, so we have this equation. Okay, let's plug this in here, okay? And it should give you delta G star. Wait. All right, so from here, I think we forgot this one here. Okay, if you do this, it's gonna give you 16. So therefore we found the expression for activation free energy. Okay, so before we cover this, let me again do some derivations here. Okay, so in our book it is said that so we know delta G star is equal to 16 pi Okay, this is volume free energy change, which is the driving force for the solidification transformation. And it is actually something that depends on the temperature. So the equation that is described in our book is like that. This is the latent heat of fusion, that is the heat given up during solidification, and melting point minus T, remember that was delta T over the melting point. So we are not given how this was derived, of course, but briefly want to show you that. So what is delta G? We talked about that is something related to enthalpy and also entropy and entropy, and there is the equation. Okay, so S is entropy. I just assume you guys know a little bit of thermodynamics here, okay? And this derivation is not important, not something I'll ask, but I'm just gonna showing to you where things are coming from. And this is gonna be, remember, we go from, when there's a melting, we go from liquid to solid, and during the melting both phases are in equilibrium, meaning they both have the same free energy. So liquid G, the G of the liquid and G of the solid has to be the same because both are stable during the melting. Okay, so both are stable during the melting at the melting temperature. Both phase is present. That's why both are stable. They are thermodynamics suggests they are both present in the structure. Therefore, their free energy value is the same. Therefore, the free energy change during the melting temperature is actually 0. So if I set this to 0, because that's the known value at the melting temperature, and I can solve with this to figure out what the entropy is, actually entropy change is. This is V. So if this is the entropy change, the definition of entropy change from a known equation, then I can go plug this in my equation here. Okay, and delta HF parenthesis 1 minus T over Tm, or okay, so that's where this equation comes from. Okay, so that shows you that this term here, the volume free energy change, is something that depends on the temperature and the latent heat of fusion, and these temperatures are in Kelvin. Okay, since now I know what this term is, what I can do is go ahead and plug in the equation, that equation here and here. So then I can rewrite the activation free energy with the temperature information included, and critical radius with the temperature information included. So that's what I'm gonna do here. So if you plug those in, what you should see is this is the R. Well, all we had done is take this and plug in those equations and rewrite these formulas here, the R star and delta G V star. And that's it, basically, these equations. Now we can go understand, because we now understood where this comes from. Now you can see that here, right? Remember, of course, if you go back, this is delta T, superheating, supercooling. How much we go below the melting temperature. So plug in delta T here, and this is what you get. Now, as you can see, our star is the critical radius, this is the surface energy, and then this is the melting temperature, this is the latent heat of solidification, and this is the supercooling. Okay. So why this formula is important? Because looking at the formula now, you can make comments like how the critical radius changes. For example, you can say, as I decrease delta T, the critical radius is increasing, right? If, in other words, the critical radius is decreasing when I increase supercooling. So the far away I'm from the melting temperature, the smaller the critical radius is. Therefore, it is easier for the nuclei to reach that critical radius because it's smaller, than make them stable. So it is easier to form stable nuclei as I increase the supercooling. Okay. So typically, we are given a typical number for the critical radius as 10 nanometer. So 10 nanometer, after that size, the particles become stable and they continue to grow. Okay, so rate of phase transformations. So the study of the reaction rate of phase transformations is called kinetics. So it explains to us the time dependence of rate. And this is, of course, an important consideration when it comes to the heat treatment, because we need to know what is the time required to achieve a certain phase at a certain temperature. And we also need to know the fraction of the reaction that has happened at a certain time period. So as a function of time, I need to know the fraction of the reaction that has occurred while we keep the temperature constant. So therefore, there are studies being done to determine the reaction rate. Okay, and how they do it? They keep the temperature constant and measure the degree of transformation as a function of time. So you keep the temperature constant, and as a function of time, let's say every 1 second, every 1 hour or something, you keep looking at the degree of transformation, meaning how much of the alpha phase, for example, went to beta phase. At 1 hour, in 2 hours, in 3 hours, how much of this alpha became beta, let's say upon cooling. So how do you measure, of course, how much of this transformation is happening? You can do X-ray diffraction to look at the species, the formation of beta, let's say, in this example. Or if one phase is conductive, you can look at the electrical conductivity. So this will tell you how, because remember, with each structure, new structure, the properties will change. So if the electrical conductivity is changing with the formation of new phases, that also tells you how much of this transformation happened. Or propagation of the sound waves may be measured, and depending on the type of system. At the end, what you are trying to do is get an information of how much the degree of transformation that has happened. So after you collect the data, you can plot it as a function of logarithm of time. What is the fraction of transformed material as a function of logarithm of time, and this is gonna give you an S-shaped curve which describes the kinetic behavior for the solid state reaction, solid to solid phase transformation. You can also see that nucleation and growth stages are also indicated. So as you can see, after a period of time, the nucleation is completed, where the nuclei became stable, and at that point the growth will start to happen. And with the growth, of course, we will observe some fraction, we will observe some material is transformed from one phase to another, and we will observe the fraction of that transformed material based on the physical property that we are measuring. And it's an S-shaped curve like this, as you can see, and it describes the time of the growth on the x-axis, and the y-axis gives us the information about the fraction transformed. So at this point right now, you can see that rate is increasing as the interfacial surface area increases and the nuclei grows. And when we come to this point, this is the maximum rate is reached. So remember here, the rate you can look at as the slope, how it is changing, right? So initially the slope is increasing, but then it is decreasing. So the maximum rate is reached in between, and then after that, after a period of time, at this point the transformation is complete. So 100% transformation from, so all alpha went to beta, for example. Okay. Of course, this experiment is done at a fixed temperature. They just, as a function of time, they just measured what is the rate of what is the fraction of the transformed material, basically, and then they plot it in this way. Okay, so for solid state transformations displaying the kinetic behavior, like shown here, the fraction of the transformation of y is a function of time, and it is expressed in this equation, what we call Avrami equation. Okay. So y, the fraction transformed, right, is equal to 1 minus exponential term minus k times t to the power of n. Here k and n, they are specific for parameters, time-dependent constants for a particular reaction. And by convention, the rate of a transformation is taken as the reciprocal of time required for the transformation to proceed halfway to completion. So that is t.5, and that is how you read the rate, okay? So when it reaches halfway of the completion. So rate is equal to the reciprocal of time required for the transformation to proceed halfway to completion. Okay, so the temperature has a very big influence on the kinetics and the rate of transformation, and we can understand this from these curves given to us, which are giving us the percent crystallization as a function of time and temperature for pure copper. And since now we know what is the rate equation, which was the reciprocal of time required for the transformation to proceed halfway to completion. So if you look at these curves obtained for the copper at different temperatures, you can see that time is decreasing with increasing temperature. So assume it's 88 degrees C. The time is right there, right? But when we go to higher temperatures, the time is decreasing. That means the rate is increasing. Okay, so the rate is increasing with increasing temperature, because the time to reach that halfway to completion is actually much smaller when we have higher temperatures, much shorter when we have higher temperatures. Therefore, if T is short, then that means its rate is high, right? So the rate is increasing with the increasing temperature. That is what these curves are telling you. It is giving us the temperature dependence of the transformation rate. Usually, under real circumstances, these rates can be so slow. So even the phase diagram might indicate a thermodynamically stable phase. For example, if I cool down, I will go from alpha to beta, right? And you expect the beta phase to show up when you cool it down. But many times this transformation is so slow, and it takes a lot of time for you to be able to observe these beta forming from alpha. So therefore, there is a possibility you might never observe that equilibrium state that is predicted in the phase diagram. Okay, let's now talk about eutectoid transformations in iron carbon phase diagram. We know that eutectoid is where the gamma austenite, when we cool down, upon cooling, it forms alpha ferrite and cementite. So of course, as in the phase diagram we are seeing, we need to go below the eutectoid temperature, which was 727, which with some degree of undercooling, we go below 727, and we know that the gamma austenite will transform into alpha ferrite and cementite, as we are seeing here. So how this structure forms, we learned about this. There is the austenite, and in the grain boundaries, the pearlite starts to form. So the pearlite is alpha plus cementite. Together they are pearlite, right? So as you can see in the grain boundaries of the austenite, the cementite and ferrite together they make the pearlite, right? They are forming. The austenite is transforming into pearlite. And of course this happened with the lamellar configuration. That is the characteristics of the eutectoid structure. Of course the cementite has a higher carbon content, so this growth happens when the carbon atoms diffuse from alpha to cementite, and the pearlite structure continues to grow within the gamma. Of course, the rate of this transformation increases with the amount of supercooling. If we look at this transformation curve, we are seeing with time how much of the austenite went to form the pearlite structure. And as you can see, when the delta T is smaller, remember delta T is eutectoid temperature minus the temperature you are at. So the eutectoid temperature is 727 minus, if this is the case, 675, right? That's gonna give you a smaller delta T compared to subtracting 600, which is gonna give you a larger delta T. So as you can see, if you go way below the eutectoid temperature, like increasing the delta T, the transformation happens within a shorter period of time compared to smaller delta T values. Because remember, this is the starting point and finishing point. This is the time. Okay, and this is starting, this is finishing. It takes longer time to achieve 100% conversion of austenite to pearlite structure when the delta T is smaller. And also you need to understand the effect of delta T. If you look at these equations here we derived, since this is delta T, okay, you see that if I decrease delta T, let's say if I increase delta T, I'm decreasing the critical radius size. So it is easier for the critical radius to be reached, and therefore make the system, make the nucleus more stable. The same thing is also valid for the activation energy necessary for nucleation and growth. Here we are seeing the delta T. When I increase it, that means if I increase the supercooling, activation energy is decreasing, which is something you want, right? You want to decrease the activation energy so that nuclei can become more easily stable and continue to grow. Okay. So based on that, we can say that coarse pearlite structure forms at higher temperatures, meaning when the delta T is smaller. Okay, so you are just a little bit below the eutectoid temperature, delta T is smaller, and at that temperatures, then at higher temperatures, we have a structure, we have coarse pearlite structure. When we say coarse, basically we are talking about the thickness of the layers of alpha ferrite and cementite. So if these layers are thick, we are saying the macrostructure is coarse pearlite. If these layers are thin, then we are saying the lamellar structure is thin. These are thinner, right? These. Then we are saying this is a fine pearlite structure. So if we have larger delta T values, we have fine pearlite structure. Remember, delta T is the driving force and supercooling. And if we have a larger supercooling, we have fine structure. And the fine structure is always interact with dislocations more, therefore providing us a better strengthening. So when you have fine pearlite structure, you have a harder material compared to a coarse pearlite, which is relatively soft, more ductile structure. So as you can see, with controlling delta T, you are able to control the microstructure of the pearlite and therefore the properties of the material. So now we're going to learn about T diagrams, time, temperature, transformation. So these diagrams provide us information about the time and temperature dependence of the transformation. Okay, so it is also called isothermal transformation diagrams. So how do they generate these diagrams? So for each temperature value, suppose the temperature here is given. So our system is again iron carbon phase diagram. The composition is 0.76 weight percent carbon, and the transformation will happen at a temperature of 675. For that temperature, we collect as a function of the time what is the percentages of the transformation, austenite to pearlite structure. Okay, so what is the austenite, the percentage of austenite transforming into pearlite? Alright, so for each temperature we collect this data. We just learned this, right? And this experiment is again, as I said, is repeated for different temperatures. So this point tells you that there is 0% austenite that is transformed to perlite. This transformation has not happened. This point tells you that 50% of the austenite is transformed to perlite. And this point tells you that 100% of the austenite is transformed into perlite. And when they collect data for all different temperatures, they can now build TTT diagrams, as you are seeing in the bottom here. Okay, so what does this show? So as you can see, in the y-axis we have temperature, and in the x-axis we have time. So it gives you information about how much time is required to achieve certain transformation at a given temperature. So suppose you want to achieve 50% completion. So 50% of the austenite goes into perlite. So here is your curve, okay? So this is showing off the 50%. So you are gonna do this at 600 degrees C. So you, in 600 degrees C, if you want to achieve 50% transformation, it's gonna take you like this, maybe 7 seconds. Okay, so this is seconds. So of course this is logarithmic scale, so not easy to read, and anyhow approximately we are saying. And then this type of information you can get. Of course they repeat this experiment. Let me erase all ink here. Okay, so what they do is they collect data for each temperature, and then they measure the points where 0% transformation, where 100% transformation happens, then put those data points here, okay, and then connect them. So this is for that this is for this temperature, but they can do it for another temperature, and these gonna be the data points. Then you can connect them, and this is gonna give you the TTT diagrams. Okay, it gives you information about the amount of transformation at a given temperature at a given time within a certain period of time. So okay, you can see here the eutectoid temperature above which we have stable austenite phase. We know this from the phase diagram, right? Above which we have austenite. Now, of course, you need to know the composition, right? The composition is given. So we are at the eutectoid composition, and above the temperature, above this temperature, you have austenite. So we have austenite stable. So remember, these are isothermal transformation diagrams. They tell you if you keep the temperature constant, how long it will take to achieve certain amount of transformation. So let's say we are at a temperature, let's say 670, right, 75, okay, 675. So let me choose another. So it will take let's say 10 seconds for the transformation to begin. At this point, of course I'm reading approximate values. Okay, it's not 10 seconds, but I cannot see. This is because 10, this is 100. So approximately, and then it will be complete. So 50% transformation will take place at 100 seconds, and the transformation of austenite to perlite will take like 1000 seconds. So after that you have complete perlite in the system. So austenite unstable means, remember, the transformation when you go below that eutectoid temperature, transformation doesn't happen. It's not like immediately from austenite perlite shows up. It doesn't happen like this. It takes time. the austenite is not stable anymore because the phase diagram says it is not stable. Thermodynamically it's showing a pearlite structure, so austenite has to convert into pearlite, but it takes time, and this diagram shows you how long it takes at a certain temperature to actually just start for the formation of pearlite and then complete the formation of pearlite, and how much it takes to achieve 50% conversion, etc. So if you go below, for example, 600, as you see, below the temperatures of 680, you see it takes a shorter period of time for this transformation to begin, because the delta T is increasing, right? We are going we are increasing the supercooling. We are going below, way below the effective temperature. So in summary, just understand that these TTT diagrams giving you information about time and temperature and correlates that with the percentage of transformation happening in the system. Okay, so how long it takes for austenite to completely convert into a pearlite at a given temperature, for example. So this type of information you can read from these diagrams. Okay, so what type of information again we can read from a diagram like this? So remember, these are giving information for constant temperature transformation in a system. So we are at a eutectoid composition we have seen from the phase diagram, and we're gonna cool it down, right? We are above the austenite temperature, 727, we are around here, a little bit higher than eutectoid temperature, and we will rapidly cool it to 627. So remember, the time is here, so I'm decreasing the temperature within a shorter period of time, so that means I'm rapidly cooling it to 627. Right there, right? So within less than 1 second, we cool it to 625. Okay, what am I talking? Okay, 625. So we started from 727, and within shorter than 1 second we decrease the temperature to 625. It is a rapid cooling, but we are seeing we still have austenite structure, because we are here in this region, right? We still have austenite structure. Now if I keep the material at that temperature, I keep the isothermal line, right? If I keep the material at that temperature, how long it will take this austenite to form the pearlite? As you can see, nearly this much time it takes. So let's say the transformation will happen here, start open here, and will end here. Okay, so at 50% transformation, you see from the austenite, cementite is forming, and then from the austenite, the pearlite structure is forming in the grain boundaries, and then it grows, and there is the complete formation, because we are in the eutectoid composition. So cementite, the austenite goes to pearlite directly. Therefore, the nucleation starts in the grain boundaries, and then it grows, and then the complete transformation happens when we reach to this point, right? This point. Okay, so this information is obtained. Of course, this was for, as I said, eutectoid composition, when the gamma goes directly to pearlite. But if you are above or below the eutectoid, hyper or hyper eutectoid, then you need to include additional lines to your diagram. So suppose your composition is 1.13, that means we are above the eutectoid, so we cannot go directly from austenite to pearlite. There is a intermediate phase here which is cementite first forms. Remember, after the cementite, the remaining here the austenite forms into perlite. So therefore there has to be information included in terms of that cementite that is forming upon cooling, and that it has to be added as an additional curve that is corresponding to that pre-eutectoid transformation. That must be included in your phase diagram. So this is the phase diagram we learned, right? This is perlite, so this is the curve, and this is perlite and austenite together when we go below austenite. But there is also needs to be cementite in the transition. So here this is pure austenite here. So when you say let's go below, we are at the eutectoid temperature, right? This one. Okay, so let's say we cool it down from higher temperatures and then keep it constant at the eutectoid temperature. What happens here is, first of all, from austenite, cementite starts to form, and then the cementite stays, but the remaining austenite starts to form perlite, right? Starts to transfer into perlite, and it takes some time, and then the complete transformation happens around this time. Okay, it starts here, but the cementite always stays in the structure. If you don't remember how the micrographs shows, like the images of the microstructure, go back to the previous chapter. We have shown how the microstructure looks like in a hypereutectoid composition. So there has to be, remember, there has to be pro-eutectoid cementite like this. Then this gamma austenite is transforming into perlite. Okay, so that the transformation is observed from here. So how much of this austenite, the remaining gamma austenite, converts into perlite? Okay, so in summary, basically, if you have working in compositions where you are above or below the eutectoid composition, then that transition compositions such as cementite has to be also included. That information has to be included in your TTT diagrams like we are showing here. Okay, so there is another product of iron carbon phase diagram which we actually cannot see in the phase diagram. That is called bainite. So this is again the product of an austenite transformation. So we have learned from the phase diagram that the austenite can transform into perlite, but that is, yes, the phase diagram tells us, but there are other products, such as one of them is bainite. What is the difference? The difference is the bainite consists of ferrite and cementite phases, just like the perlite is, but the microstructure is different. If you look under microscope, it is given to us here, bainite forms as needles or plates, and this type of structure gives more hardness to the material. So you can see that alpha ferrite is on the background, and within the alpha ferrite matrix we have needle-like cementite, as you can see. So the microstructure is different when it comes to bainite. As you can see, bainite structure is given as elongated cementite particles in alpha ferrite matrix. And we are also told it is diffusion controlled. So remember, there is nucleation and there is growth, right? And nucleation depends on the delta T, how many nuclei are forming, and energetically which ones are getting stable. but then the growth of this nuclei will depend on the atoms to diffuse into that nuclei, right? So diffusion control means the slowest mechanism in this transformation is the diffusion. So whatever the slowest rate of a process is, that one controls the overall rate. So in this case, the diffusion is slow. That's why it's controlling the overall formation of bainite. So we cannot see that bainite. It's not a stable configuration, so we don't see this in the phase diagram. But in TTT diagrams, as you can see, we can figure out where bainite is going to form and how much of that austenite will transform into bainite. So you can see these TTT curves are also C-shaped, and they have a nose here, right? This is C-shaped, and they have a nose. So as you can see, if we draw a dashed line to that nose, below the nose the austenite transforms to bainite, and above that it transforms to pearlite. So for example, starting from above the eutectoate temperature, if we cool it down much more quickly, right there, and more slower, because we can see on the x-axis what is the rate of cooling, right? So if we do that, if we are above that nose, an isothermal transformation line, all the austenite will transform into pearlite. But if we are working at temperatures below that nose temperature, the austenite will transform into bainite, rather at rapid cooling rates compared to the pearlite. So besides pearlite, bainite, there is also spherodite. Spherodite is another type of microstructure we observe in iron-carbon phase diagrams, iron-carbon alloy system. So again, you don't see spherodites indicated in the phase diagrams because again they are not thermodynamically stable. They are achieved by different cooling rates. So how does it look like? As the name implies, spherodite, this is another structure. As you can see, the spheres of cementite forming within the alpha matrix. So how this structure forms? This actually forms when you heat the alloy to a temperature just below the eutectoate temperature, such as 700 degrees C, for a long period of time, like maybe 24 hours, spherodite forms. This is again, instead of the alternating ferrite and cementite structure or the microstructure of the bainite, this cementite particles appear as sphere-like particles in a continuous alpha matrix. Another type of structure that forms from austenite, cooling of austenite, is martensite. This is a very important structure because it is the hardest structure of someone can obtain from iron-carbon alloy system, and it is observed in a very rapid cooling. We also call this quenching. For example, you take the material from an oven, it's 700 degrees C, let's say, and immediately drop it into water. Very quick cooling. We call this quenching. So from some 700, within a second, you are going to room temperature. So this is not a stable configuration. This is a not equilibrium configuration, and this is actually diffusionless transformation of austenite, because atoms doesn't have a second even to diffuse into a configuration. since atoms cannot diffuse anywhere, but they have to change shape to accommodate the carbon atoms. They are going into a different crystal structure. So what happens? The FCC austenite experiences a transformation to BCT, body-centered tetragonal martensite. Okay, so it is like this shown here. So crystal structure basically changes. If we take a look at this martensite formation in the TTT diagrams, as you can see, you need very rapid cooling rates. So you start from the austenite and you rapidly cool it down. You see the temperature is decreasing within a short period of time. And M represents, of course, the martensite. Here, when you reach to this point, you have 0% martensite forming from austenite, but here you have 50% of that austenite formed into martensite. In here, 90% of that austenite formed into martensite. So from austenite to martensite, it is a very rapid diffusionist transformation. So only slight changes in the crystal structure happens from FCC to BCT. And if we look under microscope, martensite looks as needles, and the background is the austenite. And this structure is a very hard material, very hard structure. So horizontal lines for the martensite here indicates that the martensite transformation is independent of time. It is just a function of temperature. So it here shows you. So if you have austenite, if you do slow cooling, you form the perlite, which is the alpha ferrite plus cementite. This is what we see in the phase diagram. But if we do quenching, which is a rapid cooling, we form from austenite martensite. And martensite, because it's a very hard material, it's difficult to work with or use in applications, because hard materials are brittle and you don't want the material to be so brittle. Therefore, sometimes they do heat treatments called tempering. So hold the material at certain temperatures, which lets this martensite to go into more stable phases, such as perlite. So within the martensite now, some of it turns into a perlite type of structure, therefore making the material more ductile. Again, the martensite is a single phase. It is body-centered tetragonal structure. And this was a diffusionist transformation because there is no time for atoms to diffuse around. And again, it is hard and brittle. So as we talked in the previous chapter, alloys, other than carbon, other alloying elements are added to the carbon-iron system, alloy system, such as chromium, nickel, molybdenum, tungsten, and there are reasons for that, why we add these elements, alloying elements, to the system, because we can play with the eutectoid temperature, we can change the eutectoid temperature, we can induce changes to the TTT curves. As you can see in this figure, we are seeing how that TTT curves are changing with the addition of different alloying elements. Okay, so the A represents, remember, austenite, B represents bainite, M is martensite, F is ferrite, P is perlite. In this diagram you are. So first we see that eutectoid temperature is decreased, and we also see this transformation happens within a longer period of time, from here to here. And we also see addition of elements basically separate the formation of bainite knolls. As you can see, bainite is now forming here, and this was the pearlite. So it separated two different knolls. So in summary, what you need to understand here, addition of elements all will have different effects, and addition of these elements will create changes in the TTT diagrams, which is sometimes desirable, right? Because in the processing you might want to play with the temperatures you work with, compositions you work with, or the time you work with. So it depends on what you want, and these curves will tell you therefore what are the changes induced by the addition of these alloying elements. So these were TTT diagrams. Now there is CCT diagrams. Okay, these are continuous cooling transformation diagrams. So normally the previous TTT diagrams is where we assume there is isothermal heat treatment. So at a constant, so we cool it down and maintain the material at some certain temperature, and then we can extract information from the TTT diagram, right, in the terms of the transformation time it takes to achieve a certain transformation at a certain temperature. But most of the time when we heat treat materials, we don't do isothermal transformation, meaning at a constant temperature. What we do is we continuously cool down the material. For example, we take it out of the oven and we waited for it to cool down to room temperature. So we don't keep it at a certain temperature, but rather can make it continuously cool down. So isothermal transformation diagrams, they are valid only when the transformation occurs at a constant temperature, right? So this diagram has to be modified when this temperature is constantly changing. So for continuous cooling, the time required for a reaction to begin and end is delayed. Okay, therefore the isothermal curves are actually shifted to longer times and lower temperatures. As you can see, these are the continuous cooling transformation curves where the lines are shifted to longer times and lower temperatures, where it is indicated with the solid lines compared to TTT diagrams. So these are going to be the CCT diagram, continuous cooling transformation diagram. So we are also given the cooling curves. As you can see, you start from 800 and continuously cool it down. You know the x-axis is time, continuously cooling down, the temperature is going down with time, and this is the cooling curve. The transformation will start after a time period corresponding to the intersection of the cooling curve with the beginning reaction curve right there, right? And it will end right there. So you are looking at the intersections of this cooling curve with the continuous cooling transformation curves. Okay, some examples here. The TTT diagram example. So on the isothermal transformation diagram for 0.445% carbon, sketch and label the time temperature paths to produce the following microstructures. So we're gonna produce 4 different type of microstructure, and we should be able to, from the TTT diagrams, which paths we will follow in order to achieve these structures. What is the time, temperature required in order to end up with these structures. And before going into that, I would like to mention, so remember from austenite, several different things form, right? From austenite, pearlite forms, from austenite, bainite forms, from austenite, martensite forms. So once one of these forms from austenite, such as austenite goes to pearlite, right? The pearlite now cannot transform into a bainite. So once a microstructure forms from the austenite, once the structure forms from the austenite, now that structure cannot change into another structure. So always the austenite forms into pearlite, austenite forms into bainite, austenite forms into martensite. Martensite cannot go to pearlite. If you want the material from a martensite structure to obtain a pearlite structure, you need to go back to austenite phase, heat it up, then do the required steps to achieve the pearlite structure. Okay, so just to keep that in mind, and we want 4 different types of microstructures. First, we want 42% pro-eutectoid ferrite, 58% coarse pearlite, 50% 5 pearlite, 50% bainite, and 100% martensite, 50% martensite, 50% austenite. So in the TT diagrams, which paths we should follow? That's the question. So let's start with the first one. So first we need to understand that we are talking about eutectoid composition here, because we are given pro-eutectoid ferrite and coarse pearlite structure. And coarse means, of course, you need to do the cooling slowly. So we know that we need to go below the temperature of 727, which is the eutectoid temperature. And we cannot go below 600 because below 600 bainite forms. But what we want is, we want from austenite for the ferrite and pearlite structure to form. Therefore, we need to work within the temperature range between 727 and 600. So somewhere between we can choose a temperature to work with. In this case example, for example, you can accept 680 degrees C. So first what you need to do is cool it quickly to achieve the structure. Okay, so what we need to do, cool it slowly to achieve the structure, because we want a coarse pearlite. So first we start with, let's say, above the eutectoid temperature. We go below the eutectoid temperature, which is 680. Now we need to do slow cooling to achieve the pearlite structure, right? So what I can do is keep my material at that temperature, which is 680, and it will create a slow transformation. Okay, from austenite phase, now we need to first form the ferrite, right? Ferrite is forming. It is the pro-eutectoid ferrite. And so what is this showing with the blue line is actually showing you that region where we form from austenite. We first form the ferrite alpha. Okay, so once that ferrite alpha forms at a constant temperature, we come here. Now we have austenite in the structure and the ferrite, but that austenite, if we continue to keep the material at that temperature, the austenite will form the pearlite, right? So as we keep cooling, the transformation of that austenite, besides that alpha ferrite to pearlite, will take this much, and it will be completed. So remember, now there is no more austenite in the structure. All that austenite formed into pearlite structure. Okay, so this turned into pearlite, this remained in the structure, and now the transformation happened slowly, meaning within a certain period of time. I kept it at that temperature. The structure is coarse pearlite, and now you can cool it down quickly to room temperature. It is not going to change anything in the microstructure, because as I said, once austenite transforms into pearlite and the ferrite, now there is no, even if you cool it down like this to room temperature quickly, even if you do that, even if it's coming to the martensite region, you are not forming any martensite. The structure remains like that. Okay, so if you want martensite to form, then you will have to do a different treatment. You need to go back to austenite, and different cooling treatments you need to do. So the question was saying 42% protected ferrite, 58% coarse perlite. So we can only prove that because we chose a temperature at 680, right? If you go back to the phase diagrams and read the intersection of that isothermal line with the alpha and the perlite lines, then remember we can read the weight percentages. And in fact, if you do it that way for that alloy, you can say at 680 degrees C, we are matching these composition values for the alpha and the perlite. So alpha here is the one that we formed from the austenite. Okay, so we just can prove that composition. When we work at that temperature, this composition is valid. So this is just to show if you want to achieve a certain phase with doing some certain heat treatment, can you read that information from the TTT curves. So the next one was we want to achieve 50% fine and 50% fine perlite and 50% bainite. So first of all, you need to rapidly cool the material to temperatures where you can still obtain perlite, right? So around 600, here 590. It is actually the line where the transformation from perlite to bainite happens, right there. So we quickly cool it down to 590, as you can see, and we keep the material at that temperature. So remember, this dashed line is giving us 50% transformation. So when I reach that position, from the austenite, 50% of it formed perlite. Okay, now you have 50% perlite. What are you gonna do with the remaining 50% austenite? So the remaining 50% austenite, now I want to transform this austenite to bainite. Therefore, I need to quickly decrease the temperature to the regions where bainite can form. So I drop the temperature, okay, to approximately 470 degrees C. And now what you are seeing here is this rapid cooling will not result in any of this austenite to form into bainite or perlite, okay? So what we're gonna do, even if we pass through the bainite region, within this type of rapid cooling will not result in bainite formation. So we need to again keep the material at a constant temperature. After we cool it down to 470, we need to keep the material at that temperature for bainite to form, because this way of rapid cooling from 600 degrees C to 470 degrees C will not result on bainite formation from the remaining austenite. So therefore what happens, we set the timing to 0. Okay, we set the timing to 0. So you in the time scale, because we want to record the whole transformation, so we want to start from the 0 right here. Then at that temperature, record how long it takes if we keep it at temperature to form complete the remaining austenite to bainite. Okay. So after we pass this point, the remaining 50% austenite transform into bainite. Now you have 50% of fine perlite with 50% of bainite. Now, even if you keep that temperature and suddenly drop the temperature, then no more structure can form. You set the structure already, that is 50% perlite, 50% bainite. Again, as I said, from the bainite or perlite, the martensite cannot form. Only from austenite, the martensite can form. What if you want 100% martensite? This is very easy. All you gotta do is just rapidly quench the material to the room temperature. And then you will obtain, as you can see with the blue curve, you rapidly obtain martensite. And what about 50-50? It is easy. You again rapidly cool it to the 50% martensite line, and then keep that material at that temperature, which is like approximately 290 degrees C. So then the whole structure, the all austenite, 50% of it will transform into martensite. So what about the influence of the carbon content in mechanical properties of steel? So as the carbon content increases, if we look at these diagrams here, as the carbon content increases, we are seeing that the hardness, tensile strength, yield strength is increasing. On the other hand, if we increase the carbon content, the ductility and impact energy, they are decreasing. So this is the effect of carbon content. It doesn't matter if you have hypoeutectoid, hypereutectoid. The carbon with increasing carbon content has the same effect in the structure. The same way, what about the different types of structures inside the alloy? So if you have a pearlite, if you have a coarse pearlite, fine pearlite, spherodite, all will change the hardness and the ductility. As you can see, the hardness is much higher in the fine pearlite structure compared to coarse and spherodite. So if you compare the hardness levels, the maximum is achieved with the fine pearlite structure, and the least one is with the spherodites, because the ductility of the spherodites is the highest. So as you can see, the spherodite has a much better ductility compared to coarse and fine pearlite structures. What about the hardness of the martensite? As I told you guys, this is the hardest of known materials in the carbon iron system. So martensite, as you can see, it is much harder than a fine pearlite structure. But of course this brings brittleness to the material, and tempering might be necessary to reduce this hardness and to achieve some ductility inside. So that is what the tempered martensite comes. So they are heat treated to make it less brittle, because hard materials are brittle. So what we need to do is tempering, meaning keeping the material at certain temperatures or increasing the temperature, doing some sort of heat treatment. So with increasing the temperature of the martensite structure, as you can see, the ductility increased, tensile and yield strength values decreased. This is achieved with the formation of cementite particles, which are surrounded with alpha ferrite. So in summary, we have austenite. Austenite can transform upon cooling to different type of structures. If you slowly cool austenite, which the phase diagram shows, it forms pearlite. Pearlite is a layers of alpha ferrite and cementite. Of course, it depends on what other phases forms. It depends on if you are above or below the eutectoid composition. So from austenite you can also form bainite. Bainite is also a hard phase, which is a different structure. The composition is the same, alpha and cementite particles, but then it is more needle-like cementite particles inside the alpha matrix. And if you do rapid quenching, martensite forms, which is a diffusionist formation, transformation of from one crystal structure to another. This is a very brittle structure, very strong structure. That's why it's tempered to form again alpha and cementite particles. As you see the changes, the trend of strength and ductility, the martensite is the strongest, the hardest. Then comes the tempered martensite, then followed by bainite, fine pearlite and coarse pearlite, and spherodite. Spherodite has the highest ductility, and the lowest ductility though is the martensite. In summary, we have seen iron-carbon alloy system, and we have seen different structures can form, different microstructures: pearlite, bainite, spherodite, martensite, tempered martensite, and we have seen the transformation diagrams, right? TTT diagrams, and time and temperature information can be obtained, and the rate of this phase transformation, we learned it's given by our Remy equation. And these curves are important if you want to figure out how long it takes at a certain temperature for a certain amount of transformation to happen. And also we can obtain more information, such as if we want to achieve, like the examples we have seen, if we want to achieve certain type of structure, certain type of composition, how we should approach the heat treatment, how fast we should cool it, and how long we should keep the material at certain temperature, etc. Those type of informations that you can get from TTT and CTT, CCT diagrams.